Welcome back to the second half of this EuroSea day in the Marine Data Week in the ocean race. We had a great lineup of speakers this morning. We were speaking about the importance of communicating what we do to the general public, the importance of collecting data in the right way, the importance of having enough of it, how to do it at different level of costs, how to do it in different level of technical capabilities. And in this second part, we are moving from data collection and ocean observing technologies to data products for organization dedicated to advancing technology. And Jay will tell us about high-value data sets. And
we talked a lot about collections today. We talked a lot about managing the data. But there's an essential step that is a very important next step. So I look at the value chain here, and you can see the inputs and the observations is what we've been covering. And I want to move now toward the outputs, the data and information products that really are essential to keep a customer base moving. And there's an app. Using this, then, I wanted to turn to some of the applications which you see across the top and show you. Lee and others did a very, very nice job. You can look at the physical parts. 50% of the Earth's ocean, the Earth's oxygen comes from the ocean. Without it, we wouldn't be here. Biodiversity, food, etc. But it is a 2.5 trillion annually that the blue economy brings to the global community, and it's growing. And I think the sum of that is the blue on the bottom, which says we are the foundation for health and for safety. So let's look at a few of the applications. This is one I enjoy. I acknowledge Caroline Cusack from the Marine Institute, who did this actually under the Atlantis project some years ago, in which we were looking at the data integration, which is the remote sensing and the in situ, but we add modeling to that. And from that, products are produced. Remote seas of Ireland, clearly, I was wrong. It turns out that the Irish are most worried about heat. This is off the southern coast, was concerned about the destructiveness of the waves coming off of the Atlantic. And so in the Bay of Biscay to the beginning of the Mediterranean. And in doing this, we're trying to gather data so it's interoperable, so it can be used, and then it can go and do the measurements. And the interesting question here was the use of certain of these, such as HF radar, to try and get all of the radars across the Spanish and Portuguese coast to be really interoperable so we can do transboundary work. And the results are quite nice. Here's an example. Maybe I should show you where we are. So we're in the southern part where all those black areas are. Those are the HF radar areas of measurement. And we can see here the aquaculture sites are the blue squares. And what we do is we use the HF radar. We're looking at sea surface temperature from CMEMS, et cetera, and giving forecast capabilities to the aquaculture community. And we will be also moving back toward the Bay of Biscay, north of, next to France, I hope in the next year. We have a virtual lab in Blue Cloud 2026, thanks to Dick. And we're making good progress on it. Okay, so I could continue, and I'll just do a couple of quick ones. Oil spills is so obvious I won't spend the time. And then we have coastal resilience. And here I just want to comment that there's something called the OSPAC, which is the Operational Services for Ports, which the Spanish government is doing. And they actually build port forecasts, and they give them to the ship pilots, and they're using them. And this is a nice example of taking our data, combining it into a product which is then having economic impact. Well, what's the foundation for all this? I have 1 minute left, so I'll use the 1 minute to talk about one of my favorite subjects, which is how do we build a base for all these things? to make them interoperable. And so that I look at standards and best practices. And this is a list of why do we want to even bother? One is obviously improved system interoperability. Other people have said that this morning. I don't need to repeat it. Trust in the data, compatibility. But it also helps to streamline the regulatory process, the trust in the data. And we need that in order to get people who are not specialists in our area to say, I believe what you're doing, now I'll use it effectively. And then finally, efficient use of time. Who said not relearning the wheel? That's certainly very true. And collaborative opportunities. And I just want to leave it finally to a comment on, again, coming back to EuroSea. Johannes Carstensen and George Pedahakis of Work Package 3 have been working quite hard across the various observation techniques they're seen on the left, building a history and a capability for best practices, integration, and coordination. And I was really excited to see, this is a presentation that Johannes gave, that basically in all of the areas we've been able to build up a series of best practices under EuroSea, which the broader community is now able to use. And so those are just some of the things I've been thinking about, and I think if I were to summarize, a broad range of outputs do positively impact the global marine. We need to stay connected to that. And globalization, while still catering to the local and the regional needs, is important. And we're working in OBPS and others on a global scale. I can tell you it's a challenge. It's what Taco said. Why don't people accept these things? Well, we're out in the field in Africa and Latin America trying to address those issues. So with that, thank you very much.
Thanks very much. Thank you. And we will move from these examples from the EuroSea project and other initiatives, other European initiatives, onto Simona Simoncelli's short presentation, where Simona will tell us how to use all these capacities to advance faster from the point we measure something to the point we have information about it. The floor is yours.
Thank you very much for your presentation, because actually it's helping me to go faster on mine and to integrate eventually what is my point of view. So I would like to start with a brief introduction on the how we can enhance the societal benefit of science through a community effort that collect, manage, and share data that can be acquired for a specific purpose, but that we want to deliver to the users in order to, apply them, use them for other purposes in general. But ocean knowledge and information rely on an integrated and multi-scale observation and monitoring system, and this system should be developed in tight connection with the end users and the stakeholders. This feedback with the stakeholders is important to identify which are the gaps and to continuously tailor the data products according to the societal challenges and the specific user requirements. Another aspect that I would like to focus is that we need also, the feedback in order to optimize the workflow that we are implementing. So here is a schematic of an integrated observing and monitoring system. So the tight connection that we have between the observing system with models that through assimilation and validation and calibration are interconnected. So models that are oceanographic models, circulation models, climate models, produce a huge amount of data, and these data can be combined, as was shown, in order to generate products, services, applications for the society. And these models can be used to predict the near future, the past, so we can use reanalysis to let's say, evaluate what happened in the last decades, but we can now also drive scenarios in order to, let's say, implement strategies to mitigate and adapt to the climate change. So here, another picture, another way to visualize the marine data value chain, and so how we can go from the observing system and data gathering activity to the ingestion of these data and the sharing into the blue data infrastructure that can integrate, harmonize these data coming from different sources and allow to generate products, let's say, from first level to higher level products that can drive operation at sea, decision-making, planning, and these are also important for monitoring indicators, for the IPCC panel, for example, or other kind of reporting. We need also additional data. As Jay was showing, we need not only ocean data when we are, implementing societal services or application. Here is a way, so on your left you have a data provider and the data originator that is collecting data, and you have the data manager and the data analyst that are crucial starting point to add information to the data that are gathered. So you have the raw data, then you have level 1 that is validated in an automatic way, then you have delay mode, and then you can start to have products. So from the originator or scientist point of view, you can start to produce your scientific product with a DOA, a data set paper, and a scientific paper on your data, but you can also start to share this data with the within the blue data infrastructure can be done in different ways. So through AirDAP, you can become a node of this system, this digital ecosystem. And also, there is another production phase that is coming out from the different data infrastructure. All these steps are, associated with different phases of quality control. That is at the data provider level, that is at the data infrastructure level, or at the information producer level, because we need higher and higher standards. So what is important is that what we don't want to miss is the provenance information and the quality information associated to the data. So then at the end of the value chain, we can know how much to trust the data product. Here I want to make you the example of the sea data cloud production. So we have on the left what we call the quality assurance strategy that has been implemented. So you have on top the network of the different national data center, and the exercise is to harvest all the data, temperature and salinity data within the infrastructure, and harmonize the data and do quality analysis, consistency analysis, and from this quality control analysis at the regional level, we start to deliver data sets, and from data sets we produce some basic gridded fields like climatologies, but also we started to derive other indicators like ocean content, stratification, density. So what is new in this picture? So in my point of view, the loop that is closing and always iterating, because we are in tight connection with the data providers, so any data anomaly is reported and corrected. So the quality is increasing while time is going. Then we started also to integrate the data from external sources, because we see that we are missing something like the data that have been gathered from non-European institutions. And then, the new products and all the data and products have been released through the web catalog with the DOA and the product information document. So here is just an example of this data integration with external sources from Copernicus in situ, or the World Ocean Database has increased the number and the data coverage in different sea basins. So this integration is very important. The novelty of the the data cloud was to go to a cloud environment and implement, co-design, co-develop a virtual research environment where the scientists can work in a collaborative way, but also to develop the tools so that we can share and use for this work. So from here, I want to go to the Blue Cloud 2026 project, where I will try to make a step further. So since this data integration is very important, especially for the digital twin of the ocean, what we want to do in what we call the workbenches is to implement an automatic pipeline, a workflow in a virtual research environment that is able to integrate data from different sources, data infrastructure, so gathering from this digital ecosystem. And to do so, we need to harmonize the metadata. We need to integrate the data themselves, but we need to get rid of duplicates, manage duplicates, and we need to have another quality control loop. Everything is then reporting back to the data infrastructure what we learn. We want to provide a feedback because this integration is becoming more and more easy, but also, data anomalies or other kind of anomalies that we can encounter, we want to report it back. So what are the drivers and the efforts that are needed for this? Open science approach and fair data principle are essential in order to share the data and produce information, but also fairness of software. So we now realize that the software, the tools that we need to implement in these new technological and virtual research environments are and need to be fair, to be shared with the others and reused, improved. The importance of these environments are for the training, but also for the development and co-production of essential application and products. One key point is that we have artificial intelligence that can be used to digest massive amount of data to produce any kind of product. What we want to use is to exploit this powerful technology, but relying on good data, the good data with metadata description that is supporting us to increase our knowledge. And this is it. Thank you very much.
Thanks a lot. Fantastic. So we had a great overview, what it means to come from data point to a data product. And we'll zoom in with an online speaker, Estrella Olmedo from the Spanish National Research Council. So we can put Estrella online. Hello. So you're going to give us some examples of modeling ocean salinity and using different sources of data to do that. Please take it away.
Do you see my screen?
We see very well your screen, yes, and hear you well too. Thank you.
Thank you very much, and thank you for the Simona and Jay for the very nice talks. What I want to talk is a very small piece in this whole system that Simona has shown. That is how we can generate and produce satellite products, and especially we are focused on the generation of sea surface salinity products from remote sensing. So here I have a brief introduction, which is what is the sea surface, the salinity. So salinity is the quantity of the dissolved salt content of the water. So in the global ocean, you can say that more or less for each, in average, for each kilogram of water, you can find 35 grams of dissolved salts. And what is the sea surface salinity? This is the salinity, the concentration of this dissolved salt in the uppermost ocean layer, which is the layer that can be measured by the remote sensing or by the satellite. So if you look at one map, I don't know what now, if you look at one map of the salinity, you can see that the distribution of the salinity is not homogeneous. And you can see that there are some regions of the ocean that presents lower salinity, and others one that present larger salinity. This is for several reasons. One of them is because salinity is very affected by the water cycle, or in other words, salinity can be used also for monitoring the water cycle. You can think that the ocean is the largest engine of the water cycle, because the 77% of the precipitation falls over the ocean, and the 85% of the evaporation also happens in the ocean. And both precipitation and evaporation have an impact in the salinity, such that when water precipitates, it produces a decrease in the salinity because the water that precipitates is fresh, while when there is an event of evaporation, then it produces an increase of the salinity. So that you can see that regions that are more typically most affected by precipitation present a lower salinity than those ones that are typical regions where evaporation predominates over precipitation. But also you can see that close to the main rivers months, there is a freshening in the salinity because of the fresh water that comes from to the rivers. And also in polar regions, because of the sea ice dynamics, you can see that there is a decrease of the salinity. Also, the salinity has a key role in the ocean circulation, because together with the temperature, they drive changes in density. That means that when you have an increase in salinity and decrease in temperature, therefore you have an increase in the density. So decrease in salinity and increase of temperature, you have a decrease in density, and increase in salinity, decrease in temperature, you have an increase of density. And these changes in density drive what we call the thermohaline circulation, which is a kind of motion of the waters connecting all the oceans basin that is a key tool for temperate the climate of the earth, because the cold waters are transported to warmer regions, warm waters are transported to cold regions. So, so the speed of the relevance of these variables until 2009, there was many regions in the ocean where there were very few salinity measurements. And then after 2009 started the flood program and the Argo flood system that has increased a lot our knowledge about the salinity dynamics. And you can see here now into the available number of floods and distribution of them in a map of 2019. You can see how much we have gained in terms of knowledge of these variables. So, but also at the end of 2009, started to play a role the satellites that started to measure this variable, the sea surface salinity from space, and then complementing the observational system that we have said before. And the first mission that was launched was the European Space Mission Soil Moisture and Ocean Salinity, so it's MOS. And after the launch of SMOS in 2011 and 2015. There was another mission, Aquarius, and in 2015 was launched SMAP, that is currently together with SMOS, providing a continuous monitoring of the sea surface salinity over the oceans. And now there are plans for future monitoring of the salinity from space with SIMER, which will be an European mission, which will not only measurements of the salinity, because it has several instruments on board, but especially it will collect salinity with a resolution, spatial resolution of 60 kilometers. So how does it work? So this is how it works as most. The difference, so the three satellites that are today, well, the two satellites that are, the two missions that are providing sea surface salinity, both SMOS and SMAP, but also Aquarius, are operating, so are measuring the radiation that emits the Earth in what is called the L band, so in a specific band frequency, which has several characteristics that are the first one and main one is that it is sensitive to changes of salinity. That's why we can retrieve salinity from this radiation. The second one is that it is not affected by clouds, so we can measure in this band the sea surface salinity under all weather conditions. And the last one is that this band of frequency is protected. That means that it was specifically protected for research purposes. So SMOS was the first interferometer radiometer that provided measurements of the sea surface salinity that was launched, and the principle is it generates a synthetic image by using the correlation of the different antennas visibilities in the different branches of the instrument. But because it was the first instrument that was launched with these characteristics, there were a lot of issues in the data processing of these measurements, and the first salinity maps provided by SMOS were contaminated by many sources of errors. The first one was that they appear a lot of antenna biases that hinder in the retrieval, so we had to include several empirical corrections in order to retrieve the first SMOS salinity maps. The second one was that this second reason that we gave, that the L band was protected for scientific purposes, was not so much protected. In the first maps, we found that actually it was a band that was used by some sources, illegal sources, that emitted in the same band as the satellite operates, and this produces high radio frequency interferences that produce large areas in the ocean where no acquisition was possible. And also there was another issue, that was that in order to provide sea surface salinity in the polar regions, that are key regions for understanding the water cycle, the brightness temperatures, which is the L band signal, let's say, is low sensitive to salinity at cold waters. And the last one was that close to the coastal regions, we found very large biases because of the sharp transitions between the radiation emitted over the land and the radiation emitted in the ocean. But with time, we have learned a lot how to process that. We have now almost 15 years of satellite measurements, we have developed different algorithms for improving the acquisitions, and now we have maps that can be used for many oceanographic studies that can complement all the observations provided by Argofloats and other institutes. And indeed, we have now retrievals of sea surface salinity from space in regions that at the beginning of the missions we thought we couldn't do it, no? That were out from the objectives of the mission, such that the Mediterranean Sea, that was the first semi-enclosed sea where we shown that actually by using proper algorithms we could retrieve salinity in the semi-enclosed sea. The second one was in Arctic, in the Arctic Ocean, where we first shown that SMOS were able of capturing the changes of the salinity in the main, close to the main rivers of the Arctic. And then we also see that we can see the melting of the ice, the freshening of the melting of the ice from the satellite measurements. And recently we have generated also salinity maps in the Baltic Sea and the Black Sea. And that's all. Thank you very much.
Thank you very much, Estrella. Thank you. If we have time, we will have some questions after. And now I will invite Rita Lesi from... whom I don't...
It's me. I'm
she's
connected.
online. Oh, okay. From the Euro-Mediterranean Center on Climate Change. So Rita, you to us about level...
Good afternoon, everybody. I hope you can hear me well.
Hello, yes, and we can see you very well, so it's...
Okay.
The floor is yours. You have 8 minutes. Thank you.
Yeah, thank you. So this is just a brief presentation on the sea level and the importance to study it and which data are available for its analysis. My presentation will try to tackle and to answer to some questions very briefly. So why it's important to study the sea level, how we could analyze it, which data are available to do it, and how this level is changing, and what could you expect in the future. So let's go to the first question. Why so important? If we go to the definition of sea level, of the global mean sea level, as NASA said, is the average height of the entire ocean surface. So this mean sea level could rise mainly due to two different reasons. The melting of land-based snow and ice reserves, and the thermal expansion of ocean water mass. But why is so important to study it? So first of all, the mean sea level is strictly connected to the ocean warming. So this is an information that it provided to us, and it says also how much land ice is melting. This rise could impact a lot the coastal communities from inundation and erosion. And the sea level rise happened in the past, but is also foreseen, is very likely that it will continue in the future. So the consequence of the sea level rise will include increased intensity of storm surge, flooding, and damage to coastal areas. And in many cases, this is where large population centers are located, in addition to fragile wildlife habitats. Even life further inland is threatened because rising seas can contaminate soil and groundwater with salt. And the low-lying island would be swallowed by the oceans, leading to the disappearance of large land areas and even some countries. The adaptation planning for ongoing coastal change is critical for all these mentioned reasons. But let's see how we could analyze this level and how important it is to have different sources providing information about the sea level and how important it is to consider all of them when we perform our analysis in the past and also in the future. So here you see a snapshot of the kind of data available to analyze the data, sea level data. So first of all, on the left side, you will see satellite altimetry observation covering the world ocean through the satellite. And remaining in the field of the observation, also the in situ tide gauge observations are really valuable. In situ tide gauges and satellite altimetry provides different information about sea level change. For satellite altimetry, we talk about absolute sea level, and we are at the open sea. But if we would like to consider what's happening close to the coast and also taking into account the vertical land motion, we need to consider the information given by the tide gauges. So the two kinds of observation very important for the sea level analysis are provided by the satellite altimetry plus in situ tide gauges. Both observations are included into the numerical model estimates, and this is the first source of data and information for this level, that based on numerical algorithms try to provide information for in the past and in the future, adjust their outputs to the observation available. So numerical model estimates put together not only the mathematical algorithms, but also all the observation available covering the world ocean to provide as much as possible the best data for the sea level, but also for other important oceanographic variables. There are many providers for this kind of data. Here I've reported some of them. For the in situ tide gauges, we have PSMSL and EMODNet. And for the satellite altimetry plus the numerical model estimates, we have the Climate Change Service and Copernicus Marine Service. But let's go to analyze what happened to the sea level and how it is changing. So on the left side, you will see the mean sea level daily evolution for covering the whole satellite area, namely starting from 1993 to nowadays. Here you see, so this product is based on satellite altimetry, and you will see here that the global mean sea level is increasing. But what we can see, an additional information this figure is providing to you, is that the trend computed over the whole time series, here you see that is 3.37 millimeters over year. But if you consider the 3 decades, one decade over the other, you will see that the trend is changing, and in particular that we are facing an acceleration of sea level rise. So this is a very important information. On the right side is another kind of product, but providing to you what? You will see the map of the global ocean, and colored, going from blue to red, the values of the trend of the sea level. So more red, it will mean that it's expected, not it's expected, sorry, what happened in the past, in the period of interest. So from 1993 to 2020, 22. So more red means an increased sea level. More with respect to the other areas reported with yellow or orange. But let's go to what is expected for the near future. Here I reported to you some outcomes from coming from the IPCC, the Intergovernmental Panel of Climate Change, that in 2021 published the sixth assessment report of the Intergovernmental Panel on Climate Change that is freely available online. And these figures here reports to you the different scenarios if we consider in the future what will happen to the greenhouse gases emissions. So mainly we could focus.
You have 2 minutes.
Yeah, mainly we could focus on 4 scenarios, going from very low greenhouse gases emission to low to intermediate to very high. And here you can see which is the sea level expected, the change expected for 2100. Then if we put, this is my last slide, so if we put our attention further ahead, so let's add the other 50 years, we will see, so before we were here, now we are here, that the global mean sea level rise is expected to increase further, but this is a long term, it's a longer term. I mean, it's supposed that sea level will rise for centuries to millennia due to continuing deep ocean warming and ice sheet melt, and will remain elevated for thousands of years. So this is high confidence. And if we really go into the remote future, over the next 2000 years, global mean sea level will rise by about 2 to 3 meters if warming is limited to 1.5 degrees Celsius, to 2 to 6 if we go to 2 degrees, and to 19 to 22 if we reach 5 degrees Celsius of warming. And it will continue to rise, this is a low confidence estimates, over subsequent millennia. So thanks a lot for your attention.
Thanks a lot, Rita. We have the last session, the last talk of this short session, and this will be with Francesco De Leo of the University of Genoa, who is here with us on site. And you're going to tell us about modeling ocean waves. I'm looking for your microphone, which is here, and the thing to advance the slides, please.
So thank you, Dina, and good afternoon, everyone. In these few minutes, I'm going to talk about ocean wave or sea waves data reconstruction and forecast. So basically, how can we do that? But first, why wave data are so important? Well, in fact, waves trigger many offshore and coastal processes, such as wave run-up, which is crucial for the assessment of coastal vulnerability toward inundation, or because they trigger the littoral currents when they break at the coast, so they put in motion both water and sediments, and therefore, ultimately, they're one of the main drivers of coastal erosion. So we definitely need to rely on sound wave dataset for a plethora of applications. As you may know, the easiest way that we have to describe a wave is through a simple sinusoid, which we can use to compute the wave height, h, and the wave period, t, which is the time elapsed between two successive crests. And the period is particularly relevant because it allows us to classify different families of waves, depending on their periods, in fact. Sea waves are ordinary gravity waves, with periods spanning the 1 to 30 second range. But of course, we also know that the real world is much more complex than a sinusoid. And in fact, if we try to measure the water level in a sea state like that, what we will see is a signal that is very chaotic, apparently random. So we need to use a better approach. Namely, we need to use the wave spectrum, which assumes that a sea state is made of an infinite number of regular waves, each characterized by its own height, period, and direction of propagation, theta. So if we sum up all the single layers that you can see here in this panel, for example, we can reproduce a sea state. And in turn, we can compute the wave spectrum, which tells us what is the energy content of each single component, depending on the direction theta and the period, or the frequency, which is simply 1 over the period. So all the devices that measure wave parameters, in fact, solve wave spectrum out of some sea states measurements. And the most widely used devices are, well, of course, wave buoys, acoustic Doppler current profilers, high-frequency radar, and satellites that provide sound data set of wave parameters, but they provide punctual information, so data that are continuous in time, but not in space, except for satellites that, of course, move along given trajectories. And therefore, we may need to expand our information about wave climate to get continuous data not only in time, but also in space. And in order to do so, we need to use the so-called spectral wave models, that are numerical models that allow us to solve the so-called wave action equation. So we can, let's say, we can evaluate how the wave spectrum S will evolve, both in time, dt, and space, dx. Accounting for processes related to wave propagation, so how waves interact with the bottom, for example, through shoaling and refraction, and accounting for the energy balance, so energy input, the wind wave growth, and energy sinks, so energy losses, for example, owing to the wave breaking. So basically what a numerical, a spectral wave model, what do? They take information about wind input, especially in the Mediterranean, where the main input is related to the wind stress. They take wind input, they combine information about wind speed with the geometry of the domain and the bathymetry, that is the elevation of the sea bottom, and they output through the wave model the map of a given spectral wave parameters. In this example, on the right side of the slide, you can see the significant wave height. Many services, of course, that provide, let's say, that rely on spectral wave model. We developed our own modeling chain, which I'm showing, which is based on an instructor mesh. So we developed an instructor mesh all over the Mediterranean Sea, and the resolution of the computational grid is scaled according to this sigmoid function that you can see in the upper panel. So basically, the resolution is let's say, we have a very fine resolution where it matters the most, so where the local effects are relevant, so at shallow waters. And we have about 300 meters resolution, the interdistance between nodes. And we have a coarse resolution, so the lowest resolution, where the local effects are negligible, so in deep waters, depth higher than 200 meters. In that case, we have a 20 kilometers resolution, more or less. And you can see the grid in this slide, and you can appreciate a local refinement in the Tyrrhenian Sea, which is, let's say, our main area of interest of investigation, because that's where we live and work. Of course, first we had to calibrate and validate the model, and therefore we took advantage of observation that represent our benchmark. And we used both satellite data, but especially we used buoy data retrieved from EMODNet. And you can see all the buoys that we could use in the left panel of the slide. They are highlighted through the red triangles. And on the right side, you can see an example of a comparison between model data and observations. This was the Cagliari gauge in southeast of Sardinia. On the y-axis, we have the buoy data. On the x-axis, we have the model data. And you can see that the significant wave height data line up pretty well. So once the model was validated, we could reconstruct the hindcast, so the past wave climate over the 1979-2021 period, and a forecast system that predict the spectral wave parameters on a 5-day window and an hourly resolution. So significant wave height, mean and peak periods, mean and peak wave propagation, direction, and so forth. And here you can see an example how we forecasted the Apollo hurricane that hit the Sicilian coastline in October 2021. It was quite a big event, and we were able to capture the cyclone track. So we were quite satisfied with that. So these data are now widely used, both for research and for practical applications and projects. You can find a list of papers making use of our hindcast data in the link on the top of the slide if you're interested. And here you can see a list of the latest projects that use the forecast system that mainly concern water quality assessment and harbor operativity, so the safety of shipping, basically. And I would like to conclude this talk by showing you a quick animation of a platform that was developed in the framework of the SINBAD project that you can use to access our forecast data of wave parameters and a bunch of other parameters such as water temperature, salinity, and so forth. And that's all. Thank you. With just a few seconds. Now here you can access data for, let's say, only for the North Iranian Sea, but then of course we have data all over the Mediterranean Sea that are freely available upon request, but not directly uploaded on this platform though.
Fantastic. Thank you very much. You can leave it running at the back. It's nice. So we are almost at the time of moving to the next session. But I just want to have one question for the audience. If you have a burning desire to ask something from our previous speakers, you can use this opportunity now. Oh, we are back on track, and we start the second session, the following session, where we're going to be speaking about data assimilation techniques to improve forecasting. And we have only 4 speakers, and then we have a coffee break. So we have now first speaker Ronan McAdam, also from the EuroSea project and from CMCC, who's going to tell us about the current state of the art of marine forecasting and how does it depend on the observations. Ronan, the floor is yours.
Thank you very much. Thanks, everyone. Thanks, Dina. Thanks for the invitation. Let's see if I can work this. Yes, I'm going to talk about the state of the art of marine forecasting. So far today, we've heard a lot about the long chain of work that goes into preparing observational data, from the taking it to the management of it, the sharing of it, etc., etc. What I do in my role is I take these observations and I apply them, and I like to think I put them to good use in preparing forecasts and validating forecasts. So let's see a few examples of that. So let's start with the basics, the pillars of forecasting. I think it's clear that observational data in one way or another affects every part of the forecasting process, from the actual dynamical modeling, which depends very much on our understanding and our ability to recreate with equations and code the dynamical processes. And of course, that is somewhat due to our ability to observe the ocean. The observational data itself then is directly assimilated into the forecast. So of course, to predict the future, you need to know the current state of the ocean. And that's why you take your observational data and you create an analysis or a reanalysis, a reconstruction of the current state of the ocean, which in turn forms your initial conditions. And the uncertainty in the initial conditions then, of course, impacts the ensemble of the forecast, gives us a measure of uncertainty of the forecast. So I'm sure we all agree that it's necessary everywhere. And of course, something I don't show on the slide, but at the end of the day, you need to validate your forecast, and you need consistent long-term data. And in some cases, you need high-resolution regional data, depending on the forecast system. In some cases, you can get away with lower resolution, but global. So we'll see a few examples of that. So I've called it "you are what you assimilate," and I think there is a metaphor here with diet and the phrase "you are what you eat." If you consider a short-term forecast, and here's an example of one there, of the SST in the Mediterranean taken last summer during the marine heat wave. We're familiar with short-term forecasts. You need 5 days, 10 days advance. Okay, you need high-frequency temporal data there, and so as a result, that determines what sort of in-situ data you need to input as your initial conditions. So I consider that, if we're using a sport analogy, I would consider that a sprinter. Okay, you have to, you're concerned about short time scales and being very precise. On the other hand, you might have something like a seasonal forecast system, where instead of going for precision and identifying when an event might occur in a particular hour or day, you want to have an seasonal average or aggregate view of let's say, the likelihood of a marine heat wave happening or the number of total days in a 3-month period. And with seasonal forecast systems, they're quite different fundamentally to other forecast systems. They are usually an ensemble of components, model components. You have the ocean, you have the sea ice, you have the land, the atmosphere, and they all have to speak to each other. They are coupled. And so I would consider that more of a football team, where on its own, one component might not be the best in the business, but together they make the difference. So now in EuroSea, we advanced the application of these types of forecasting systems to the marine environment. One message I would take away from this is that, historically speaking, if you consider atmospheric forecasting and ocean forecasting has always been trying to kind of keep up with atmospheric forecasting in terms of quality, resolution, but also in terms of applications. If you think about how many climate services there are for agriculture, for tourism, that make use of seasonal forecasts of atmospheric data, we wanted there to be the same for marine forecasting. So let's have a look at a few activities we undertook with the short-term forecast of the Mediterranean, and I should say this is the Copernicus Mediterranean physical system produced partly at the CMCC. We've been looking at marine heat waves in parts of the Mediterranean, in particular last year, and we found that our analysis, which in turn becomes the initial condition of the forecast, agrees very well with the observations and captured these extremes. And we also did another study on the actual forecast, and we were able to predict with great precision the onset and decay of marine heat waves. The same model is also very good at capturing these acqua alta events in Venice. So this is usually sea level, high sea level mixed with high tide in the Venetian islands, which can cause quite devastating flooding and economic damage, of course. And you can see here that last November, the forecast captured the peak acqua alta to an accuracy of 1 centimeter, which I think is very impressive. So for short term, these are some interesting new developments, and so far so good. For seasonal forecasting, we have a different viewpoint. So you can't measure, as I said before, to the same precision, but you can still get useful information because your lead time, your early warning time is much earlier. So we still consider marine heat waves, but this time we asked the question, well, typically marine heat waves are studied with sea surface temperature. Because we have the data available, we have a large amount of satellite data. But really, marine heat waves do the damage below the surface. So if you consider marine species, they move vertically throughout the ocean, throughout the day, to dozens of meters, and if you consider the damage to coral reefs, for example, that occurs well below the surface. So we need something that's more user relevant, whether that user is a marine protected area or an aquaculture farm. We said, let's have a user relevant indicator. So let's look for the first time at the subsurface. So we did that. We took seasonal forecasts of the surface, which you can see at the top left there, and seasonal forecasts of the subsurface ocean, looking at the upper 40 meters. We find that this infamous event in the Northeast Pacific there, known as the blob, which actually was extreme heating, which lasts for 2 or 3 years, we found that if you considered the subsurface, you find that the extreme event actually lasted longer than you would have if you considered only the surface. So the actual record of extreme events is different, and also the forecasting skill increases when you consider the subsurface. So the subsurface ocean, we argue, is not only more important, but actually more predictable. So why not use that in an early warning system? Likewise, for the Mediterranean, we found that, again, for 2003, which is one of the most infamous events on record, the subsurface event looks very different. So there was only a small part of the Mediterranean near the Gulf of Lion and the Ligurian Sea, which experienced a marine heat wave. And generally, as you can see on the right, the subsurface is considerably easier to predict on seasonal timescales than the surface. So the message there is, previously the Eastern Mediterranean would have been considered a region where we couldn't apply an early warning system, but if you consider the subsurface, you actually can. And I think that's an important message for stakeholders. So I will end with a few other advancements in EuroSea. some of which we've seen before today, but I think they have a few nice messages for seasonal forecasting. So we've seen already the aquaculture farm in Danish farm in Ireland, where there has been a co-development with stakeholders of in situ monitoring and forecasting. And as we get to the end of the EuroSea project, we've only just started talking to them about seasonal forecasting. I hope that conversation will continue into the future because there is interest in seasonal forecasting. And I think this co-development is a really key word and a really key process to make what we want to say are user-relevant products. In EuroSea, work I wasn't part of, but my colleagues at CMCC were, on the assimilating of new means of observation. So we've seen some quite exciting new potential means of observing the ocean today, and one day they could eventually be assimilated into forecast systems, therefore reducing uncertainties. Lastly, something that happened during EuroSea, but was perhaps not our responsibility, the Copernicus Climate Change Service, whose forecast we use, they have made, for the first time, available ocean forecasts, ocean seasonal forecasts, not just SST, but salinity, mixed layer depth, subsurface. So now people can go away and do similar studies to what I was doing with the subsurface marine heat waves. And I think this, making it accessible, will really open the door to a lot more studies, because I was very lucky. I managed to do what I did with marine heat waves because we had the data in-house, and I stumbled across it one Wednesday morning, and I thought, yeah, this is a good idea for a research. If it's available, then many more people will have that idea and that opportunity. So availability is key. Thanks, everyone.
Thanks very much. Fantastic message. Next speaker will be Francisca Campuzano from Atlantic Collab. You're going to tell about applications for blue economy. You have 8 minutes.
Okay, thank you very much. Thank you very much for the invitation. I had to reckon that to speak about this subject for general public, like it was the idea, it's a difficult task, like as data simulation in 8 minutes. So then what I thought is to try to show you, to illustrate some of the work that we did in the past, and sometimes that was really important for us, and where we demonstrate the capacities. And also the relationship that we have numerical models with the numerical models with the observations, because sometimes when we think on assimilation, we always think in integrating the data, and there are other ways that we can interact with that. So I want to talk about the blue economy, especially because most of the activities, we know they are long-term activities, but most of them take place in the coastal area, and it's very difficult area for doing data assimilation. And I will try to show you some of the things that we need very good results there, and are where many of the risk takes place. So this is an image from Copernicus Marine, and then when we go to the ocean, you can assimilate all the data, satellite, Argo, float, altimetry, everything, to try to produce global ocean forecast. But then when we go to the coastal area, this is a bit more complicated. So then I went back to the concept of data simulation, that is the discipline that seeks to optimize combine theory, numerical models, with observation. So when I look at the coastal area, what I see that we are doing a lot of assimilation, like meteorological models are using observation that they assimilate. We have then open boundary conditions that we integrate in a way of assimilation. Then we have also the land boundary conditions that we assimilate, that they are also observation. Well, in this case, we are having this near real-time serving from the MonNet, and then in Copernicus on the other side. So there is a lot of assimilation, a part of inside of the hydrodynamic or coastal model. Then also downscaling, because we go sometimes from these global models to the required area of the specific where we have the application for the coastal economy. So we can go to any detail, I mean, at the scale of meters, but we can replicate this method with many times. So just to give you an idea of what are the processes that we have to cope with in the coastal area, especially in the Atlantic, is different from here, that this is an example of the Lisbon area where we have the influence from the ocean, but then we have the input from the river that brings a lot of problems, like brings also contaminants, pollutants, everything. Other small rivers that we don't consider that important, but then they have a critical importance there. We have a small mountain range that we are not considering in general models that can generate shelter areas. We have upwelling processes. We have then different kind of use, like this is a marine protected area. We have flooding. We have bathing waters. We have oil and other substances spills, erosion. And then it's a very dynamic area because we have the plume of the estuary going out and in. It's changing all the time. It changes with the tides, changes with the rain, everything. And then we have observation like HF radar, things like that. And just to show you that I'm not making this up, this is also in Lisbon, the city center flood for combined tides. This is the route that they pass in front of Lisbon also, so they have a lot of probability of oil spills, and also you can see some erosion in these bathing waters. So coming back to this integration for the river, what we are building also within ModNet is trying to have near real-time data of the very important stations. Not all of them, because if not, we go crazy like with this map. So then to try to have the most important ones in a common format, metadata, one-stop shop, all following conventions, everything. And try to have most of the rivers, not only the major river, but as most as we can, and try to include the estuary mixing. That is something that we are working now on it. So just to show you the state, this was 1997. Oh, no, 2007, I think. Or 2017, sorry. Well, this, and then you can see how it is now. This for Europe is relatively well covered. The Mediterranean, still there are some gaps there. But we are moving globally. This now is for the States and Canada, and also we have some in the southern hemisphere, like from Argentina. We are the first one we have in this area. And then, just to show you, we try to acknowledge the source, but just I wanted to show you this image. If you are using a climatology, in this case, this is the Ebro River in Spain, you can see that it's 4 times the discharge in one day. So if you are using climatology, the impact in the coastal area will be very big. And then these discharges, they have their importance. Here we can see some event that took place during last year. We were contacted by a municipality because during the bathing water season, it rained, and then there had some coliform pollution in the coastal area. So they wanted to know which was the source. So even these minor rivers has a big impact. This is another example. It's a little bit earlier. In the Algarve, there was an toxic algae bloom detected in this area near Faro. We made some simulations and that doing forecast, and the result is that they took decision to close the bit. So I'm trying to show you some examples that are really, they had an impact in how they were built. This is also another known case, one of the very first operational oceanography that we did in the group in Portugal in collaboration with the Galician people for the Prestige. So people went to look and to collect the oil spill based in those forecasts. I mean, and that was, we lost money at the time because we have a server that was limited. We couldn't broadcast that many information. Then we recovered, so that's why I still am here. But it's a very good example of, if you have a very good assimilation or use of the data and very good source of information, you can really do an impact. You can see here a comparison with the satellite image, so for validation it was quite good. Then another way that we can interact with the data is like this. This is an HF radar in the coast of Portugal. Maybe we don't need to integrate in the model, but to run the model on top of it. So this is a Lagrangian tracer that we can use for oil spill or for other things. And we are running on top of it, and then when it reaches out the area of the HF radar, it continues with model. And then, because we are in the ocean race, I brought a couple of examples of cases with boats. This boat was a person that disappeared in the Azores. No one knew about it. And then we were deriving areas of search and rescue. And even if the search and rescue is not very, very precise, for someone that is doing this kind of job, if instead of saying going north, going south, you are reducing 50%, which is a lot. And this was the simulation, and is where it was found was in the center, very close to the limit of the simulation. And then another one is, and I'm happy that Cassie is here, and you will talk with her on Friday, for the mini boat. This is an example of a mini boat in 2013 a mini boat that was released in the States, going to Portugal, and then they wanted to know where it was going to arrive and at what time. So it was not destroyed by hitting the rocks. And then we did this simulation that worked quite well. So either you can see here the mini boat in the center, in the waves. So someone was there at the time, waiting for it. And you can see the person going down the cliff and entering the water and collecting the mini boat. So we was perfect simulation for us. And then managed to rescue it and has some minimal damage. But if we were not there, I mean, this is a good example of if you have the right type of data, you can do it. And then we are also now having our own ocean race, mini fleet ocean race. That is 2 mini boats that we released last month in the Canaries, and Cassie was in one of the launches with me there. It was a pleasure to do that. And we have, this is the 5th of May, it's IFADO 3. And on the 19th of May, IFADO 4. But then IFADO 4, even if it was released afterwards, is going ahead. Because IFADO 3 decided to do a monitoring campaign during 3 weeks next to La Palma Island in the wake of the island. So even if it's low-cost citizen science, it's a very good example of, I mean, probably it's the longest campaign in that area. So, I mean, like 3 weeks monitoring the water day and night. I don't know if there is so many examples like this. And well, that's it, everyone, that I wanted to tell you today. Thank you.
Thank you very much. Excellent. So we'll continue speaking of weather conditions with Antonio Parozzi from SEMA Research Foundation. You will tell us something about high-quality models for localized needs. Please, have 8 minutes.
Thank you so much. I'm going to give a very quick overview about what we are doing so far, also in cooperation with other Italian and European research institutions concerning the use of data simulation techniques for the prediction of high-impact weather events. The starting point is very simple. It's starting from the evidence that we know, all of us. We have observational data and also projection data telling that the Mediterranean atmosphere is getting warmer and warmer. This is one very interesting interactive atlas developed by PCC, just zooming on the Mediterranean area in terms of mean daily temperature over the region, and the signal, despite the spread due to different model ensemble, is very clear. But not only the Mediterranean atmosphere, in some sense, is getting warmer, but we are also aware that the Mediterranean sea surface temperature is getting warmer, and it is projected by the end of this century to achieve a value of more than +3 degrees. All in all, those informations already in those days, in the current situation, are making very complex the work of people, experts, dealing with day-by-day prediction of extreme weather events. And indeed, the Mediterranean area is very rich on extreme weather events. One of the most popular, in even if probably not most wanted by weather forecaster, are the so-called mesoscale convective systems that I mentioned also yesterday in another brief speech. Those events are typical all over the Mediterranean coastline, especially in the northwestern one, and they are events that are capable to pour down in a few hours huge amount of water, in the order of 400 to 300 millimeters of rainfall in a few hours, and also capable to produce tremendous lightning activities. Those are the, this is not end of the year celebration, but it is just lightning activities in those events all over the Mediterranean coastline. But we don't have only to do with those extreme events. We have also to do with some new entries. Colleague from University of Genova before mentioned the Mediterranean Hurricane Apollo. This was a very intense event that took place at the end of October 2021. If you look at the image without paying attention to the neighboring region, it looks like a tropical hurricane. We know that the physics is different, but just the visual pattern is very similar. And we know that those events, because of climate change, there are studies around suggesting that, especially in this region, which is the Gulf of Sirte region, will become more frequent. And we have also, in some sense, if not new entries, something that usually is not expected to be observed in the Mediterranean. This was an event happening last year in August. It developed as a derecho, starting from the Balearic Islands, and it moved like a line of convection along the Mediterranean Sea, affecting first Corsica area, then Liguria and Tuscany. And this event was lasting until the Austria area, and it was capable to produce hailstones in the size of 12 centimeters. So this was a very intense event, capable to affect deeply human activities and social activity. It costed 12 people losing their life because of extreme winds and extreme hailstones. And it was an event, like a summary of those that I was mentioning, that really put a lot of stress on our predictive capability test. In the sense that if you we're looking at the prediction that very same day using standard weather predictions, you had in the middle of the event this kind of pattern. This is the pattern of the maximum reflectivity predicted around 10 UTC on that day. And yes, you could expect some severe convection activity in the Pianura Padana area, but not certainly the big monster, convective monster that indeed developed. They were active at the level of the Italian Civil Protection Department, alert in terms of yellow alert for severe thunderstorm, but not for such an organized system. The only way in which we could get a decent prediction in indicast mode later was triggered by a specific question of this guy. We are indeed in ocean race, Giovanni Soldini. Giovanni Soldini was having his own boat in northern Tuscany. It was under maintenance in Massa Carrara area. And his boat was basically brought away by the wind, by a wind peak of 140 kilometers, and partially destroyed. The event was very intense, and just to give an idea, I don't know if the animation started. This is a camera, not in Massa Carrara, but in Sestre Levante, a camera located in the local harbor, and those are the hailstones. Good enough, nobody was around, because most of the people were still sleeping, but those are hailstones in the size of 5 to 10 centimeters falling down into the harbor. The person installing the camera did a very good job because the camera resisted, was still there at the end of the event. But at a certain point, because of the downburst which developed that day in front of the derecho, you are completely losing the sense of what it is water and what it is atmosphere. Okay, at a certain point, it is completely, in some sense, a mess and completely mixed up. Then what we try to do, we try to predict this event. We try to put in place the assimilation of radar data, lightning data, and maybe we could consider at a certain point also to think about to simulate sea surface temperature into the model. And we ended up with this, in Italia, with this result. In the first part, the derecho affected the Eastern Liguria region. This is the maximum horizontal wind at 10 meters, and this is the vertical velocity in terms of updraft. By assimilating in rapid update cycle mode lightning data and radar data, we could get a very good prediction, and at a certain point, when the event was affecting this area, we can indeed create properly the system. This is a few hours later, the more developed derecho moving towards the Tuscany coastline. And also in this case, by profiting of the WRF model operated at 2.5 kilometers, assimilating in rapid update cycle mode the data, we could get a very good forecast. The point is that this was feasible only with 1 hour of anticipation, basically. So it is purely nowcasting. But it is probably the way to go in order to tackle those events that will get more localized and more intense. We are not working yet on the assimilation of oceanographic data like sea surface temperature, but maybe this can be the place to establish synergies, cooperation, to explore also that part. I'm sure that the forecast probably can get even better.
Thank you very much. Fantastic. So keep your questions if you have any after the last speaker of the session, Stefania Siliberti. We have a few minutes of Q&A. So Stefania, you're from Nalogin Oceanic Weather Systems. You're going to tell us how regional modeling products are improved to meet the user requirements.
Thank you, Dina. Hello, everyone. So the idea of this presentation is somehow to drive a sort of storytelling from our today's session on the capacity of using observations for improving near real-time products for the ocean. So basically, oops, is the first one?
You put down, yeah, the down.
Ah, the down, sorry, sorry. Okay, so basically at Now System, Nalogin Oceanic Weather Systems located in Madrid, we basically provide technical support, scientifically based for services and know-how for support marine and coastal applications. And of course, somehow our path is driven by the operational value chain. So we are deeply involved in the development of the Iberian Biscay Irish Monitoring and Forecasting Center that is within the framework of Copernicus Marine Service, together with Mercator Ocean International, Meteo France, and the Supercomputing Center located in Galicia. But also, we have a strong component from the in situ thematic assembly center, being somehow responsible of the operations, validations, and data delivery of specific observations, in situ observations in the EB area. And of course, we develop also added value service in the framework of the product quality activities, but also a training material for, let's say, trying to demonstrate how to use properly marine data for building new services. I will mention also another initiative in my second part of the presentation related on the support on the Ocean Prediction Decade Collaborative Center that somehow opened the window of how will be the future of our value chain. But this, of course, is completed by a specific attention at the coastal scale, and in this framework, we are launching some pilot applications supported by the Copernicus Marine Service in the area of, in the Galway Bay, in the Ebro Delta, and in the Gulf of Biscay. But now let's have a briefly look on what is Copernicus Marine Service. This is one of the programs of the initiatives within the Copernicus Earth System Observation funded by the European Commission and implemented by Mercator Ocean International for providing free and systematic, reliable, scientifically based products representing the state of the ocean for the blue, the green, and the white components. And in the Iberian Biscay Irish Monitoring and Forecasting Center, as well as in the other, let's say, regions that are provided within the Copernicus Marine Service, we deliver a quite complete product catalog that encompasses both near real-time analysis and forecasting systems together with ocean reanalysis from 1993 to 2021 that have the scope to, let's say, perform some climate studies and ocean monitoring indicators calculation that are fundamental for understanding and analyze basically the region and the climate impact in the ocean particularly. But of course, let's say the pillar is related to the operational ocean system architecture. This is a nice picture that is included in the guide that has been delivered in the framework of the expert team of operational ocean forecasting systems as a joint action between GOOS, IOC, and WMO. And it shows briefly how the three main pillars of our forecasting system works together. So we have the first step that is related on the collection of the observation and access to upstream data in order to provide the best initial condition for the forecasting cycle thanks to the let's say, implementation of numerical models together with data simulation schemes that basically have the possibility to ingest all the available observations in the ocean and improve the initial condition for our forecasting cycle. Then we have the numerical model that performs the short-term prediction of our ocean state, and at the end, the products are delivered to users. In the case of the Iberian Biscay Irish Monitoring and Forecasting Center, basically we are adding the complexity of managing and interconnecting the three major components, the physics, the waves, and the biogeochemistry, in order to provide to user the best and the most comprehensive information about the ocean state in the European Atlantic area. And in this case, particularly where the data simulation is working. Basically, it's working on, let's say, improving the capacity, the accuracy of the forecasting products for the waves and the physical model by ingesting available satellite, significant wave height for the waves, sea level anomaly, and sea surface temperature from satellite together with the temperature and in situ profiles for the physical component. And of course, the benefit that is taken by the biogeochemistry model is through the coupling interface. The three systems, just to mention, that are nested in the global monitoring forecasting system, so in the analysis and forecast system provided by Copernicus, and of course we have direct access to all available atmospheric forcing provided by ECMWF, as well as EMODNet for the access of observations in the area that are as well used for performing validation exercise. So after the calculation of the running of the model, all the products are further validated through operational procedure. This is basically an example on how by improving the data simulation schemes, by ingesting new observation, we are able to improve the forecasting system. You see below the root mean square difference for temperature at between 0 and 5 meters for the physical component, and you see in the light purple the new version of the operational system that entered into service in November 2022 that has a reduced error with respect to the previous one, while on the right you see basically the advantage of assimilating CFOSAT spectral data in the wave model with respect to the control run by improving the slope of the best fit. Of course, and very briefly, the main drivers here are, what? Sorry? The presentation, okay. The main drivers here are related on the way we are providing such products. Of course, the modeling framework is a science-pooled evolution, is based on science-pooled evolution. So all the, let's say, improvement that we are going to include in the Iberian Biscay Irish Monitoring and Forecasting Center have a solid basis in the numerical framework by increasing the resolution, upgrading the numerical model core, as well as evolving the data simulation assimilation, without forgetting the importance of having a look on the coastal zone, where the usage of artificial intelligence techniques really made a difference in the way we are going to improve the forcing at harbor scale, but also providing let's say, wave climate projections at ports. And just as a final message, I would briefly talk about Ocean Prediction Dedicated Collaborative Center. These are the slides kindly shared by Enrique Alvarez, that is the technical coordinator at Mercator Ocean of this initiative, that works around the motto connecting the world around ocean prediction. And what we are going to do. So basically, the idea is really to implement a framework that is inspiring the UN decade by moving from the ocean forecast we have to the ocean forecast that we want. And we want, of course, much more connections among the community and service, and designing much robust system worldwide. And this is done basically by fertilizing and catalyzing the effort at global scale, considering also the specificity of each region. And here you see that the GOOS regional alliances are, let's say, playing a key role, but also by establishing a group of experts that is now identifying the gaps and working to understand the ways forward for improving the operational value chain in a way that may exploit in the next generation of operational system much more the concept of digital twins and interoperability. Thank you very much.
Thanks very much. Thank you. Put them here. So we are at the end of the session, just before the break. Are there any questions to our speakers? If not, I have one. And maybe the speakers of both two sessions can share something, but very, very briefly, like a quick tour de table. I will not invite everybody on stage. I have a question. How will modeling and data assimilation evolve in a changing climate? If you have one priority to name, what would it be from your point of view, from the point of your expertise and experience? Where do we want to put the efforts? For the collaborative center, for example. You can start, Stefania.
Of course, I mean, here the main game is to understand how we need to change our value chain in the way we are now, let's say, we know how it works. The 3 steps are the 3 fundamental pillars for building an operational forecasting system. And of course, here, the way we are going to integrate high-resolution observations requires, of course, an advancement from the modeling point of view in order to, let's say, improve the numerical schemes, and at the same time improving the numerical kernel for addressing processes at small scales. And the effort that we are doing, I mean, that in the framework of the Ocean Prediction Decade Collaborative Center we are promoting, is to, let's say, make the step forward, in the sense understanding which are the gaps, understanding what we have, and today we have a quite, let's say, complete overview of the capacity that as community we can afford with the observation and with the modeling, but at the same time trying to, let's say, make the service science-based and much more user-oriented, in the sense that we can exploit more the concept of the digital twin and provide also additional information to users to understand the socio-economical impact of climate change in our regional and coastal scale. For instance, this is one of the, let's say, of the main messages.
Anyone else on the modeling priorities in the changing climate? Thanks, Stefania.
Well, not the modeling priorities, but to tackle climate change. I think that speeding up the release of data, new observation, verify, validated, and ready to be assimilated in the models is very important. So we need to push as much data as possible to the forecasting centers, and it is very important to integrate and assimilate different platforms, especially to tackle the coastal ocean, and also to deliver like ocean monitoring indicators for climate change, like oceanic content. So this is very important, and we are not, let's say, performing 100%. We can still do something to speed up this process.
Thanks very much. Anyone else on the topic? Francisco?
Thank you. I like it very much, the presentation that was just behind me, because I think that this is very interesting, this assimilation in the meteorology. I think if you can improve any of the products that are used by the model, not only the model itself or assimilating the model, that will make that we are able to provide this answer, because I believe that what you were observing at the atmosphere place, it will have an effect also on the circulation. So then if you improve, even in the, sometimes when we are talking about some local problems with, at the scale of several meters, we are talking about sometimes meteorology of 2.5 kilometers. So we are still sometimes also a bit far between one each other. So I think that this is something that where there is a lot of room for improvement, in my opinion.
Thanks very much. Okay, let's close. For now, we have a coffee break until 4 o'clock. We reconvene sharply at 4. I think it's better when I'm here. And I would just to ask the speakers to stay. We take another picture. We took one in the morning just to have then we may compare who's in. Yeah. For that. So everybody back at 4 o'clock, please. And speakers stay with me for just 1 minute for a picture. Thank you. All right, so welcome back. Take your seats. I will invite Valeria to be with me here for a little slide intervention. If you remember Slido, we had some questions for you, and we have some more questions for you. Take your phones. We need the Slido slide. Please, with the QR code and the code, the hashtag.
Okay, thank you. We do still have our QR code and our number, but we have some more questions, some more polls. So this kind of session on Slido is going to be related more to the closing, the final words of the day, and also... Okay. If we can go to the first question. This is going to be related more to the ocean products, so it's going to be related to the first half of the afternoon that we've had. So if you have something to say, do it now. And also we are going to have another... Okay, just a couple seconds. Maybe, yeah, we can use this minutes for people to come back in.
It's the live stream.
Yep.
Okay, but still for people here, we can start looking at the screen.
Yes.
Getting connected to Slido, please.
Dopo? Okay. Okay, we have a little bit of a technical issue, so we're going to go Slido after the first session. So maybe
after,
okay. 10
okay.
minutes, and
yeah,
we can start. And yeah, so keep your Slido open. It's going to arrive.
Okay. We adjust and adapt ourselves. So okay, again, welcome back, everyone. Take your seats. Be comfortable. These are two last short sessions for today. We finish in 1 hour. We have discussed all sorts of different aspects of the value chain of marine knowledge as we look at it in the EuroSea project, from data acquisition to modeling, forecasting, data assimilation. Now we're going to go into the specific services, elaborate a bit more. We've already seen some of them. And this session now will have 4 speakers telling us about forecasts and data applications for fisheries and aquaculture. I will first invite Ove Nidberg from the Institute of Marine Research in Norway to tell us about the multi-use of ocean space for aquaculture. You want to say something else? Okay, I am only about today. But please, surprises.
I can take the other one, but yeah, this is good. This is good. That is the right one, and do you hear me? That's excellent. Where do I go forward here?
Oh, it's on the chair, yeah.
Thank you, Chairman. Thank you, Antonio. I got the right presentation, and at least that was a relief. Tomorrow, I'm going to talk about an Olamur project. Some of you know me as the coordinator of that project, and I collaborate with the people here, Antonio, Giulia, and Beatrice, and others. But today, I'm going to talk about a Norwegian national project called the SFI Smart Ocean. It's not a project, it's rather a large program involving a large series of industry, mostly on sensors and communication devices, but also at end users in the oil and energy industry and aquaculture, and a wide range of research institutes centered around the University of Bergen, the University College of Bergen, and the Institute of Marine Research. So our vision for a smart ocean is that we have sensors at aquaculture farms, oil gas rigs, offshore wind farms, pipelines, and cables. because there are so many marine installations out there now. We have to utilize that we have actually installations all over the North Sea, all over the various seas that we operate in. We are particularly concerned about the North Sea and the Norwegian coast, of course, but this center is in truly general, and we like to think that the things we work with are generic. So our vision is that these various installations have sensors, not only cable sensors, because we can all put out cables there, but we can't put out cables everywhere. If we communicate wireless, if we can communicate via the Internet of Underwater Things, we have a lot of observation points, and we can gather information from various places. From aquaculture is in the middle here, but also for oil rigs, from shipping, and from demersal sensors. But transferring data is difficult. So we have put up an experimental facility outside a research station in an archipelago west of Bergen. This is the Austevoll facility. It was built up originally as an aquaculture research station and has also evolved into a marine biology, an experimental marine biology station where we do a lot of various marine biology work, and especially regarding research and also regarding pollution, etc. Now we are using technology as the third leg to stand on for this vision, for this installation. On this, to the left here, you can see there is an aquaculture farm in the middle. You can even see the bottom tomography, the bathygraphy of the area. And we have sensors on each side. You don't see much of it, but on the top of the sensor is a GSM sender. We can communicate via 4G. We have to have some way of communicating which is absolutely reliable. But the goal is not to communicate via 4G. The goal is to communicate underwater via acoustic modems. Here is the area. The aquaculture facility and the research station is in this area, and you have rigs on different area around here. So the test rigs are, at the moment, 2 separate rigs communicating with the GSM 4G network, but we are testing acoustic submerged modems. An extra rigs is going to be installed, and so are demersal rigs. Another possible test areas are also present in the Bergen areas. We're not bound to this area, but the goal is to build up an experimental facility to test various sensors and various installations in order to communicate. A central part of this is the CCAT temperature, pressure, and conductivity recorder, and an acoustic current Doppler profiler, an ACDP. Both of them transfer data in almost real time. Actually, the GSM sends data every 10th minute to the central, which is also connected to clouds. One cloud from the Onderås instruments. We have delivered part of the instrumentation, and one cloud belonging to the Institute of Marine Research, which is the Norwegian Marine Data Center that some of you collaborate with. In addition to this, we plan an expansion of the Austevoll test hub. Right now, we are focused in the area around the station, but we have expanded and got permission to install various test hubs, various sensors of different kinds, some with a unit on the surface, some demersal, some floating at different depths. And these nodes will be set out in the years to come, testing various new equipment here. Here you can see some examples. The floating rig is to the left, whereas the acoustic Doppler profiler is in the middle. And to the right, 2 gentlemen from the Norwegian Defense Research Institute are testing an acoustic modem made by the Kongsberg Group. But we are going further. We are testing this, the observatory I mentioned is placed in a fjord environment at Bergen. And fjords are rather special. Not many countries have that kind of geological formations, but they're quite difficult to operate in. And if we can make acoustic modems to work there, they can in principle work everywhere. So the next major step will be to develop the high Arctic ocean observation system. Combine Smart Ocean with an independent EU project called the HIAOS, serving underwater observations of the ocean and the sea ice, including acoustic thermometry and point measurements. New mooring and acoustic technology will also be used north of Svalbard. The aim is that this observatory will operate independently for 1 year under the polar ice. Note that these sensors will be placed we will use an icebreaker belonging to the Norwegian Coast Guard in order to set up the equipment. And they are under the polar ice, so you cannot go to the surface and communicate out there. It's a rather demanding area. So the objective is to develop a nested multi-purpose acoustic network. But we also, in addition to this, do integrity monitoring of constructions belonging partly to offshore oil and gas and partly to offshore wind industry. Those parts of the center is mainly done by those industries themselves. But what is common to them is the communication measures and to some extent also the sensors. So a lot of challenges emerges for this smart ocean. You have to ensure that there are reliable real-time observations. Acoustic transfer has to be done in real time, but you have to select data. You have to use artificial intelligence in the sensors to select the data because, of course, the amount of data that can be transferred via acoustic modems is very limited. And then you have data transferred to cloud and ensuring the quality control of sensors and data. We also assess impact of marine life by sensors and modem. In general, fish are not affected by these modems. However, we do believe that there is some impact on marine mammals. There are urgent needs regarding surveillance of infrastructure. Yes, one of them is, of course, the integrity, but also is the possible sabotage and damages of cables, which means internet cables, and of course everybody has heard of the North Stream. So I end my presentation with this. This is our website of the center and my email address for those interested. Thank you.
Thanks very much, Owen. Fantastic improvisation. Okay, so Giulia Dapuet of University of Genoa is now going to join us to tell something about how you identify new sites for fisheries.
Yes.
Please, the floor is yours.
Thank you. Good morning, everybody. And I will talk you about an application here in the Ligurian Sea about fish farming, and more exactly marine offshore fish farming, so the breeding of fish, of marine fish in open sea. No. Okay, thank you. So fish farming is an activity that is an expansion all over the world in order to meet the growing demand for new marine food. For this reason, it's fundamental to identify new suitable sites for this activity in a perspective of marine spatial planning and sustainable development. For this, we have to consider at the same time environmental, social, and economic aspect. But what is a suitable site? We can define it as a site that maximizes the growth of fish and minimizes the impact on the surrounding environment, minimize the interaction with other users, other activity of the sea, and from the economic point of view, minimize the cost. So it is, site selection is a very complex sustainability problem that we have to face in some way. In Italy, we have a technical guide that was released in 2020 by the Italian Institute for Environmental Protection and Research, ISPRA, that support local administration in the assignment of marine zone for aquaculture. Before, in 2015, as a University of Genoa, we conducted a study here in the Ligurian Sea for site selection of a suitable site for offshore fish farm. So these are our starting point. Now, in Liguria, we have a project, Atlante del Mare, Sea Atlas, that aims to improve and promote aquaculture. And in particular, we are developing a procedure for identify and classify suitable area for marine offshore fish farming. So we are developing a system that will support the decision makers in special management and special planning. The heart of the procedure are the definition of constraints and suitable criteria. Constraints allow to exclude the area where the farm cannot be installed, while criteria allow to classify the suitable area into a suitability scale. But going more in deep, which are constraints? Are the area that can be a source of pollution, of impact for the farm, the area that can be impacted by the presence of the farm, the area where there are some interferences with other activities, and the area with prohibitions. So, this information excludes area where we cannot install our farm. Then we have suitable criteria that are regarding the feasibility of installing the farm, so geological and oceanographical information, optimal condition for fish growth, so chemical physical characterization of the water, environmental quality, and a socio-economical evaluation. We are now testing our procedure in the Gulf of La Spezia, that is in the eastern of Liguria, and it is a typical Ligurian and Italian area with a very, very high naturalistic and ecological value, but on the contrary, and also as a consequence, a very high urbanization with a lot of human pressure. So it is an area very, very complex to manage. So this is our first result. In red, you can see the suitable area. So all the areas that are suitable for install in the area of La Spezia fish farm. Now we have to understand which of this point is the best one. And for doing this, we have to consider as a fourth thing that each criterion, so all the criteria that will allow to discriminate area has a special variability. As you know, for example, temperature has a special variability, so each point has a different value, and this is the first information that can tell us if an area is better than another one. Second information is that each criterion has a different importance respected to the suitability of an area. So, for example, we have to understand if it's more important the condition, optimal condition for the fish growth, or is more important, for example, the socio-economical evaluation. For this, we will involve experts and stakeholders that, thanks to the experience, tell us what is the importance, the weight of each criterion. And now we are in this step. So this information allows us to classify area. I report here an example of the previous study that we conducted in near Portofino. And now, now we are in this situation. So we have a red map, and we would like to characterize the area with a sustainability scale from red, that are suitable area, to blue, that are optimal area. Okay, so this is the system, the procedure. For doing all this, we need data. We have data that came from different components. We have a social, economical, and ecological aspect. We have a static data, dynamic data. Most of the data that we used came from the regional geoportal. Liguria have a geoportal with a lot of data. And some data comes directly from the project because we are conducting monitoring. And few data also came from Copernicus and Edmonet. So I conclude, tell that this system will support the fishery chain, and in particular support the spatial planning, improving the sustainability of the activity at a local level. And thanks also to the availability of data, we can update the procedure and continuously give new update results to the decision maker. Thank you.
Thanks a lot. Next speaker is going to be joining us through a video. So we have just a record from Dorothy Dunkel from Synth of Ocean. She's going to speak about aquaculture as well and really focus on the sustainability of aquaculture.
My name is Dorothy Dunkel, and I work at Synth of Ocean here in Bergen, Norway. And I want to talk a little bit about sustainable fisheries and aquaculture, what we're doing now, today's state of action, and what we need to do to get the future sustainable ocean that we're absolutely dependent on. Now, the UN Sustainable Development Goals, the SDGs, are our frame for sustainability. But the big question is, how do we go from global to local? And what we see is that the synergies and the local action plans are best formulated when we look at the targets. You see in the circle here, there is 169 of the different targets of the SDGs, but some of the SDG targets are more relevant than others when we talk about fisheries and aquaculture. For example, Target 2.C ensures stable food commodity markets and timely access to information. Target 4.3, very important for fisheries and aquaculture as in regards to equal access to affordable technical, vocational, and higher education. Target 9.4, upgrade all industries and infrastructure for sustainability. I'm going to show you an example of that in a second. And target 14.7, increase the economic benefits from sustainable use of marine resources. Now, we are just starting a new blue revolution, and it comes all into play when we have the technology. That makes us possible to rethink how we use and multi-use ocean space. But this cannot come into the real space without investments. Public-private partnerships are essential to make the ideas a reality. An example of this is the North Sea Farm 1, which has just been started. Construction hopefully is operational by the end of this year from the Netherlands and North Sea farmers. And this is growing seaweed within a wind farm. Now, seaweed has growing international markets and it has a good nutritional value, market value. But more importantly for the climate, it sequesters carbon. It absorbs the carbon that the ocean is already absorbing and makes this kind of blue carbon aspect a reality when we can scale it up. Now, this was put into place with Amazon's Right Now Climate Fund, 1.5 million euro grant. Amazon has 100 million euros in this fund, and there's many other examples of big corporations that want to invest in technology for a better ocean and a better climate. But how do we merge this idea of technology and the blue revolution with the EU goal of a sustainable blue economy? The answer here lies also in the SDGs and the understanding that the blue economy is a ecological, social, economic, technical system. We have to also put people in the center, that jobs have to be available, they have to be inclusive across different nations, walks of life, and genders, that ocean health is human health, that we really understand that we are inextricably connected to the ocean. And then we can start thinking about the sustainability aspect, and how, when we are so connected, how do we stay connected in a sustainable way? We have to harness this technology and share data. Sharing is caring. And we have the efficiency project that is just wrapping up now, a EU Horizon 2020 Research and Innovation Action, where we were trying to answer the question, how can we most efficiently feed our fish? And to do efficient feeding, we really have to understand fish behavior so we don't overfeed. Feed is like the number one biggest bottleneck for sustainability for aquaculture. And so by setting up different sensors and different cameras, we learn how the fish feed, and we can feed more efficiently. We also have been partnering with Ovum, Hauge Aqua, formerly, with their semi-closed containment system, this amazing egg that is now in the water. I think there's 6 of them, where we also are putting cameras to understanding how Atlantic salmon feed more efficiently. And this is giving us huge returns as far as money saved and more sustainable production. But what good is data if we can't share it? Now, the NC Seafood Innovation Cluster, Norwegian Center of Excellence here in Bergen, has the AquaCloud project. And AquaCloud has over 300 now companies playing in sharing data. People understand that their competitive advantage is learning from shared data. So it's not hiding your data. That's not your advantage. Your advantage is sharing. But we also understand that there's always a limit to science, that experiential knowledge from civil society and business actors can be very important for a sustainable ocean, because science can't do everything. And we have good examples of doing higher quality assessments and co-developing, for example, ocean plans, climate plans with citizens, and getting people engaged, going from the global to the local, having the local time invested, but also that local knowledge that is so important for the contextualization of sustainability. We've been working with the sustainability cards, the SDG cards .no, that has all the 169 targets in there to work with different businesses and society members on exactly these issues, sustainability, and bringing it to local. So our future ocean has to be sustainable, nutritious, and plentiful. The ocean has our best high quality fats and proteins, and that has to be accessible. Digital data collection has to be efficient. We need new predictions and digital twins for better understanding of scenarios of multi-use and use in the ocean, but also restorative fisheries and aquaculture, that we can do multi-trophic aquaculture, that monoculturing is not the best way in many parts of the world for a more sustainable, less impact, higher quality protein and diverse market sustainability. And we need fisheries and aquaculture that support the positive environmental, social, and cultural effects for the ocean that we want. Thank you very much.
Great talk from Dorothy. We need a lot of data for sustainable fisheries and aquaculture, but we can also use fisheries to provide data. So that's the transition to the final talk of this short session, with online joining us Lohitzoon Labirieta of Asti, Spain. Please apologize for the pronunciation. You can correct me. The floor is yours.
Hello, good afternoon. So thank you for the introduction. My name is Lohitzoon Solabarrieta. And today I will present you the Sustentech project. And as you were announcing, this is the final step of the metocean data measured on board fishing vessels to be published in ocean global data repositories. So in our case, we have in the Sustuntech project, we have 2 fishing vessels that we use as marine observing platforms to measure data and create data sets to be publicly published in data repositories or data aggregators. So as I was saying, we take advantage of 2 tuna fishing vessels that operate in the Indian Ocean. And we use tuna fishing vessels because usually they are highly instrumented and they already have a lot of sensors to measure different variables that could be interesting for us to be published in ocean data portals and fill some of the gaps that exist nowadays. So to create data that will be interoperable,
sorry, you are not sharing slides, just to let you know.
No?
Yeah.
Sorry?
Okay, just thanks.
No? Can you see my screen?
Yes, now we see it, yes.
Okay, so as I was, maybe I can continue.
Maybe let's not restart, maybe just start from the sharing from the point where you were. Okay,
yes,
excellent, thank you very much.
Okay,
Thanks.
so sorry for that.
6 minutes left, yes, thank you.
Okay, so as I was saying, we are trying to create a data set from fishing vessels, and we will create data management plan for all the data sets to make the data fair, to follow the FAIR standards and make them interoperable for future uses. So Sustuntech project has different objectives, and today I am focusing just on the work package 4, which aims to provide ocean data sets to fill the gaps that we know that we have in the open ocean seas, taking advantage of these fishing vessels that operate in different places of the open oceans, and they will be benefited also from the improving of the data models that will be improved by the data that they are going to share with the global ocean models. So this is the data flow that we have been following in the project, and we summarized it in 5 steps. So the first one, we had to decide which essential ocean variables were going to be useful for us to make the data selections. Then we had to make the processing and validation, following always the FAIR principles to finally create the data set and make them available through open data portals. So this is, as you can see here, we made a group, 3 groups for data sets that were measured by different sensors. So the vessel already had some sensors. Then we had the X-band radar data that usually is used in these vessels for safety reasons. And then those fishing vessels are deploying some buoys for the fishing strategies. And all of them, they are measuring some ocean variables that could be valuable for global ocean data portals. And we decided that we could create interesting and useful data sets, current and wind temperature data sets from instruments already installed in the vessels. We could also measure wave and surface current information from the X-band radar data installed in the vessel. And finally, we could create sea surface current data sets or product from the buoys that are deployed from the fishing vessels. So what was the first step? So the first step was to take the data and think how we were going to analyze them to make them findable, accessible, interoperable, and reusable following the FAIR principles. So to make them findable, we will findable and accessible, we will upload them to open ocean data portals, and we will assign a DOI, so they will be findable and accessible. We are following all the quality control, the standard quality controls to make them interoperable, and we are adding rich metadata to the data sets together with the data management plan and product description documents to make the data interoperable and especially reusable for future times. A few minutes ago, a lot of sensors, and here you can see that they have ADCP, they have the X-band radar data, they have thermometer, anemometer, and the only thing that we included was the Ratatosk processing the computer to create a data flow between all these sensors and our center and create the data chain. And let me show you some of the data products that we already created. So this is an example of the wind data from the vessel anemometer. We have created 2 data sets, one for each of the vessels that we have. And in the plot, you can see that the correlation between the vessel data and the global models is really good. And we decided to remove some directions due to the geometrical position of the anemometer in the vessel. We also created data sets from the thermometer on board the vessel. And here again, we created 2 data sets, 1 year in each of the vessels. And we can see the variability, the interannual variability of the sea surface temperature. And again, we have really good agreement with satellite measurements, taking in account that what we are measuring is single points and the satellite information is an aggregated information. Then I insisted at the beginning the FAIR principles because we wanted to use the ADCP on board the vessel to create a current data set in different levels using the onboard ADCP. But we, at the beginning of the project, not all the required metadata were included in the data chain. So after doing all the analysis, we have realized that we will not be able to create a proper data set, but we already know what to do for next project or next time or next people who wants to create data sets from the vessel's ADCP in the vessel, and we will make this document publicly available together with the rest of the data sets. We are also creating surface velocities product from the drifters deployed from the vessel. And in this case, instead of giving punctual information, we are giving aggregated information in different spatial points in the Indian Ocean to create a data set according or following to the data provider requirements, because we have to consider all the requirements of the data provider, which are not always the same as the scientific purposes. And finally, as I was announcing, we have also processed the X-band radar data. The X-band radar data are used by the vessels for safety to see possible obstacles in the water, but we can change a little bit the configuration of the radar to retrieve surface currents and waves information. Sadly, we were not capable to install the radar in the vessels because of the physical problems in the vessel, but we have do the testing on land. We had the radar for 1 year in the west coast of France, and we have seen that we are capable to create a good data set. And in fact, we have created this data set and data set from the buoy-derived currents and wave information from the X-band radar are already updated to the AirDAP data server that we have built in the project. And why an AirDAP data server? Because we have considered that it provides a lot of advantages, not only to upload the data, but to download the data and to create a machine accessible server to offer to the users and to download the data sets, the subsets of the data sets, the variables that they want in the formats that they would like to download. So the AirDAP server has been the selected way to publish the data, and we are in touch with EMODNet. We will share the data with them. We will publish the data through Zenodo to assign a DOI, and next step will be to share the data to the rest or to other ocean data global data portals. And to conclude, we have seen that fishing vessels can be used as metocean data providers, doing the pre-selection of the essential ocean variables that we want to measure, and following always the FAIR principles. And this is all. Thank you very much.
Thanks a lot. And we are entering the final session for today with several talks on oceanographic services now, not for fisheries aquaculture, but for ports and cities. We are here in the harbor. Let's look a little bit more into this kind of applications of marine knowledge. I will invite first Bruno Del Sal, who is joining us online, and I'll just announce the order of the speakers. Then there will be Begonia Perez and Giovanni Copini, both speaking of OSPAC tool and EuroSea, and the final will be with the live speaker with us, Alberto Capata. Now, okay, Bruno Del Sal from AIVP Association, bringing together urban and port stakeholders. Please, the floor is yours.
Thank you so much. Do you see my screen? Yes, I think all is okay for you. Thank you so much for your kind invitations today to represent the IEVP during these very special days for Genoa. It's the grand final of the Volvo Ocean Race, very prestigious. It's an honor for me to be with you for many reasons. First, Genoa is one of the founding port city of the IEVP and always one of pillars of our international network. Second, without port cities, this race today could not exist. Third, without the fantastic city port ecosystem, the level of innovations will not be the same to imagine these Formula Ones of seas. The IEVP, International Association Citizen Port, was created in 1988. In the beginning, we were less than 10 European port cities, and today we are 119 members located in 100 different port cities all over the world. In the beginning, the associations mainly worked on the questions of waterfront with a very urban point of view, and we have progressively discovered all the potential of the city-port relationships. After the summit of Rio in 1992, we have integrated in our reflections all the environmental questions, and the IEVP became, at this period, the first organizations of ports questioning the environmental stakes. In the following years, during the 90s and the beginning of the 21st century, we assisted to a very quickly development of the globalizations with a very important new logistic concept, the just-in-time. And during this period, port and port cities progressively reorganize their territories to welcome the new giants of seas, developed IT, adapted their organizations to work always quicker and efficiently. Finally, in the past 10 years, more or less, with the creations and the development of social network and internet, we have observed the emergence of citizens in all debates regarding port projects. Therefore, we have progressively started to encourage our members to create port center as a dedicated scientific equipment to explain to citizens what a port is and why the port is very important in the daily life of each one. Sorry to have remembered this short story, but it perfectly shows as the city port ecosystem is more and more complex, and as the number of stakeholders that act in this ecosystem is higher each day. Today, pretending to be a resilient or efficient port city, of course, you must propose to your client modern terminals of containers, break bulk terminals, general cargo terminals, logistic platforms, etc. But you must also be able to manage the biodiversity in all basins of your port, to reduce the noise and air pollutions, to develop skills of your citizens for the new job sports, to upgrade the quality of life of the populations, to respect the maritime identity, to prevent effect of the climate change, to imagine new zero carbon mobility, etc., etc. To help our members meet all these challenges, we are working with them to draw up the AIVP agenda for sustainable port cities. It was adopted in 1988 and has since been ratified by more than 100 organizations, more or less. 1 month ago, for an example, the City and Port of Montreal committed to implementing it. This agenda is broken down into 10 goals, all of which correspond directly to the 17 SDG of the United Nations. For each goal, we have set out 4 or 5 concrete actions, and we are currently developing a public policy assessment tool that will be made available to our members. Of course, as international organizations, our aim is for our members to make continuous progress towards a sustainable port city. And to do this, we are identifying best practices and disseminating knowledge as widely as possible. I'm going to give you in 3 or 4 minutes, very quickly, a few examples. Regarding the goal 1 of our agenda, which concerns the climate change, we can see on the slide 2 classical examples, one in Rotterdam. Rotterdam, the port and all the stakeholders of the place develop Porto's carbon storage project, and it's very, of course, important for the future. And one other example may be different. In USA, in San Diego, with a Spanish society, eConcrete will provide shoreline stabilizations, protect against coastline flooding, and improve the water ecology of the bay. On the goal 2, other examples. The goal 2 is regarding the energy transitions and circular economy. We observe actually in the world 2 main tendencies in this domain. The first one is the development of shore power equipments in the different port cities. It's the case of Barcelona, Seattle, LA, Le Havre, Hamburg, etc., etc. And a lot of innovations to use wave and wind for the new productions of energy. It's the case in Portugal, Israel, Gibraltar, Valparaiso, etc., etc. Always a goal too,
Bruno,
but
you have 2 minutes.
regarding the circular economy stake, one example in France, in Strasbourg, where a port policy encouraged synergy between companies in the port area to optimize the use of resources and rivalries solid waste. Of course, there is a lot of other examples, but I can develop today a lot. On the goal 3, for example, sustainable mobility. In these points, port cities are also very innovative. In Helsinki, we have the port developed a smart traffic system to reduce the impact of cargo coming in ferries. And in Valparaiso, there is a very interesting project with a logistic platform outside the urban area with integrated cargo control and bureaucracy and a call system avoiding traffic bottlenecks in port city. It's very, very important for the quality of life of populations. Another example, very topish of the idea defended by the AIVP, the goal 8 regarding the port city interface. This picture has been taken in Lexos Matosinhos in Portugal, and this equipment is a cruise terminal, but not a simple cruise terminal, but it's also a landmark in the skyline of Matosinhos, very iconic building. And in this building, we have different functions, 3 functions: port activity, of course, with cruise, university and research center, and in the same building, a lot of space to organize professional events. So it's a typical example of what we can do if we imagine to combine the functions of ports and the city. The goal 9 is very classical, and the health and life quality, and we can see on the slide different examples to enable air quality, to optimize the consumptions and management of fresh water, etc., etc. It's in Rotterdam, it's in Valencia, Rotterdam, Balear Islands, etc., etc. Last example, other topic, very important, the biodiversity, and it's a goal 10 of our agenda. In Rouen, in France, or in Buenos Aires, Argentina, you can see on the slide efforts made by the city port to ecological restorations of port spaces, etc. So to develop new public space for the citizens and to have a very mixed use of the space. To conclude, for all these challenges, of course, cooperation and co-constructions are key points. We must imagine together solutions of the future for all services which concern ports and oceans. Even if, for many stakeholders, to do together is still a new paradigm and a long way, we have no other choices. Time is now coming for a very common approach of port and oceanic stakes. Share our experiences, diffuse our knowledge, pool our resources. It's a key point for the success and for the future. For sure, it's a role of international organizations like IEVP to concretely act day after day to help our members all over the world to build the sustainable port city. I don't know if we'll win the battle, but after 34 years, our motivation is intact. Thank you so much.
Thank you very much, Bruno. Of course, ports are the interface, the ultimate interface between the city and the sea, and a fantastic opportunity to co-design across sectors. In the EuroSea, we have done some of that as well in terms of oceanographic services, and I will invite Both Begonia Perez from Puertas del Estado in Spain and Giovanni Copini from CMCC Italy to join forces presenting the OSPAC tool that was developed through the EuroSea project. Go ahead, please, Begonia. We can hear you. We can see you if you say something.
Okay.
And we can hear you. Excellent.
Hello, everybody. Good afternoon. Can you hear me well?
Yes, we do.
Okay, perfect. Thank you very much. Well, I will share my screen. I'm sorry, 1 second. Now. Okay, can you see presentation mode? Okay, so thank you very much for the invitation to this event. It's an honor for me to be here and in representation of Puertos del Estado, which is Ports of Spain organization. And also, I hope I will have the opportunity to present also our collaborative work with other partners in the Horizon 2020 project EuroSea, and in particular the development of the OSPAC tool. OSPAC means Operational Services for Ports and Cities. I will start first with an overview of the ocean observing and forecasting system that we have implemented in Puertos del Estado for the last 30 years along the Spanish coast. And I will show how from this experience and this history we have progressed and moved in recent years to the downstream services and fit-for-purpose products we had developed for our ports, and now in EuroSea also for the ports and the cities. So I will start by showing, first of all, the two main components of our observational and forecasting system. The first one is the Puertos del Estado observational component, which is composed nowadays of 25 open ocean and coastal buoys, 41 tide gauges and meteorological stations, and eight HF radars providing surface currents along the Spanish coast, as in the map you can see on the right. We are measuring the main physical parameters, which are waves, sea level, temperature, salinity, currents, but also wind and atmospheric pressure data for the last more than 30 years. We started with the first measurements in the 80s. And with the main objective of this system, in situ observing system, is to have available real-time observations, but also historical time series in order to perform climate studies and assess the evolution of these main variables. As an example, we have wave data since the 80s, for example. These data are essential for issuing warnings for our ports, for the numerical models validations, and as I said before, also for climate studies. And this network was especially focused originally on the needs of the port system for design of infrastructures, but also in terms of operations. Nowadays, these data are being used by the whole community, not only in Spain, but also from other institutions outside Spain. But we have, of course, in parallel, worked significantly all these years in the forecasting component in Puertos del Estado. And for that, we started with regional scale forecasts of waves, as you can see in the left picture, or sea level, as you can see in the right plot, that have been working in particularly the wave forecast since 1995, and the sea level forecasts with these regional scales since 1998. Here you can see an example of the sea level forecast for Barcelona port, where the tide is very small, but when you have a storm, you may have sea levels significantly larger than during good weather conditions. And these are forecasted since 1998, as I said. But Of course, in recent years, we have made an important effort on improving the resolution of our models to really approach the needs at the coast and at the port itself. And for that, we have worked intensely in downscaling and developing of coastal and harbor scale downscaled models. Most of them, the ones of waves and circulation nested in the Copernicus marine forecasting systems. And for example, nowadays we have high resolution models of wind with resolutions reaching up to 50 meters, or high resolution wave models reaching 5 meters inside the ports, and high resolution circulation models reaching 70 meters also in the port domain. In summary, in the last years, we have now more than 80 operational models running at very high resolution, combining atmospheric wave and circulation models for 44 ports. And this is something that has been achieved over the last 10 years, thanks to a Spanish project that which is named Samoa, the Samoa Initiative. But then we have developed the next important step, which is the downstream and outreach and integration of all this information by developing tools and creating downstream services that really are possible to be used by not only by the ports, because we are already providing data to all the community, but also to the general public, but of course with a special focus always in our case on ports requirements. And for that, for example, for many years, since many years ago, we are providing warnings of waves and sea level or sea level oscillations, even combined warnings on waves and sea levels in our website. We also provide real-time data and forecast and climate data and products that are integrated in the Portus system, which is a visualization tool that combines all the data coming from the different models at different scales and from all existing in situ observations of the system, of the port system, in order to provide visualization of the tide forecast, statistics of the more probable direction of waves, trends in the different variables, etc. This is a tool that we have developed for all the Spanish coast, combined with an application that is now very popular for mobiles, the name IMAR. But again, in recent years, we needed to move from these downstream services to a more tailored tool developed specifically for the ports. And this has also been done in the frame of this Samoa initiative I mentioned before. And for that, we have developed a specific tool, which has been the basis to the OSPAC tool that we have developed in the framework of the EuroSea project, expanding this service not only to the port, but also to the adjacent city. So let me now describe briefly what is this OSPAC tool developed in the framework of EuroSea. As you can see, we have worked in this tool in collaboration with other partners, including No-Logging, which is a co-developer of the software, but also the National Oceanography Centre in the UK, the Centre Euro-Mediterraneo sui Cambiamenti Climatici, the CMCC, which is Giovanni Copini, one of the main authors, but also other institutions in Colombia and the ports authorities of Barcelona or Taranto, as you will see. So the idea of this tool is, OSPAC is to create a one-stop shop or service aggregator that is able to move to the very local scale on the need to fit the user needs and requirements in terms of services. And this has become a new coastal management product that allows to improve the environmental management and the hazard warning at this very local scale. But also, as I mentioned before, a very important aspect of this tool is that we have extended it to not only to the needs of ports, but also to the cities. And the idea we have in mind behind is to drive forward this concept of a smart maritime city by strengthening this port-city connection. We have also integrated in the framework with EuroSea novel sensors and observations, and of course, a state-of-the-art downscale model forecast as the ones developed by CNCC or the University of Barcelona in Catalonia. Here we have an example of the sensors recently installed in Barcelona, which provide novel measurements of waves and sea level inside the port, and which are very important for validation of the system. In the framework of the project, that has combined the software development with model downscaling and instrumentation, we are implementing demonstrators at 3 pilot sites, which are 2 in Europe, 1 in Barcelona, Spain, and another 1 in Taranto, in Italy. And we are also working in implementation of this tool in Buenaventura port in Colombia. In the case of Barcelona, we had the hard launch of the tool already in March 2023, and we had attendance from the Barcelona City Council and the port, and a lot of interested city and port users attending the presentation of the tool. So what is it and how does it look like? Well, this OSPAC tool is really a common infrastructure that integrates in situ observations and model forecasts, as I mentioned before, in order to provide the following main applications that are already in place, as you can see here. First of all, the visualization of real-time ocean data from different instrumentation in the port or the city, the ones available at that site. We also have an application is to visualize the forecasts 3 days ahead based on the downscaled high-resolution models I mentioned before, some of them developed in the frame of the EuroSea project. And we can do that for specific points in the domain of the harbor and outside the harbor, but we can do the visualization, of course, of in the form of maps. For example, you can see here an example of, I think this is waves or currents. I don't see very well, but you can see in a way forecast maps or forecast points. We have also the possibility to have access to specific modules like the floating debris module or the oil spill module that allow, and finally we have also the possibility to have access to real-time and forecast warnings by email. So with respect to the real-time in situ observations, this is absolutely configurable by the users that can subscribe to specific real-time and forecast points. They can define specifically the thresholds for the different variables and receive tailor-made warnings. So this is designed to be configurable by the final user at the port and the city. And then they would receive this type of warnings by email as the one you can see in the screen. Here we have an example of the 2 downstream services based on the current forecasts that you can also access through this tool, which are specifically important for the ports, like the oil spill or the floating debris that I mentioned before. So finally, thank you. This is all with respect to this tool. This is how the front page looks like. As I said before, we have already this operational in Barcelona and Taranto, and this has been selected by the European Commission Innovation Radar in 2022 and 2023. And as final message, I would like to say that the idea of this tool is to go down from the science to the final users and from the regional to the coastal and local scales, to design fit-for-purpose products and tools that we have developed in collaboration with the ports and the cities, and integrating of novel sensors and state-of-the-art models. Thank you very much. This is all.
Thanks a lot, Begonia. It was fantastic work in EuroSea. And we have Giovanni Copini online as well to say a few words on the tool if he is connected. Is he? Not connected. Okay, well, in this case, we will move to the last speaker of the session. I will invite Alberto Cappato from Porto Antico of Genoa. Thank you very much.
Thank you. I'm not really the last one because I will ask to Antonio to join me on the floor. So first of all, welcome in Genoa for the one of you that are not from here, and welcome in the new waterfront area of Genoa. As Bru del Sal told you some minutes ago, waterfront are very special places where innovation lives in a quite interesting way. And here in Genoa, you have the opportunity to see the first season of waterfront, the Porto Antico area, that is not far away from here, about in the west direction, that was renovated more than 30 years ago by a project with the same architect that is now building the second season of waterfront. And this is quite interesting to see the difference, because Porto Antico renovation that has been made to celebrate the 500th anniversary of the discovery of America. It was the same period of the Barcelona waterfront. We took example to new waterfront that were renovated in the United States, Baltimore or something like that. And this was a process that was very, very important, that helped to change how can I say, the city. Genoa was a port city, an heavy industry city in the image of people, and thanks to that operation, Genoa changed completely and is now also a touristic destination, a quite interesting destination with an heritage of buildings, palaces that are very, very great. And this was the first challenge at the beginning, and the challenge was to not keep all these spaces empty after the exhibition. And it was a success. This is a success that is studied all around the world, that a very successful operation of renovation. And now we have a new challenge, and we are now in the area of this new challenge of the waterfront of Levante, that is completely new, 30 years after the first one. And there are a lot of differences in the project, the sustainability aspect. Also the green. If you go on the other side, we have no green, we have no shade. That's a problem with all the challenge we have with the sea level rises, climate change, hot. And here, the project is totally different. Now it's not already finished, but you will see that the green is trees and are really well conceived. So what we need to do, because we have a competition from other areas, touristic areas in the world, because with the low-cost flight, a family from Milano, or a family from Venice, a family from Lyon, may decide to go with the same amount of money in Dublin for a weekend, in Genoa, or in Rome. So our competitors are not the other waterfront in the Med or somewhere else, but so we need to do things to become more attractive. And thanks to Antonio and a group of Genoese companies, we built a quite interesting project. In the past section, you talk about data. And when you have to manage an area, a touristic area that has more than 4.5 million visitors each year, and you want to make things to make the attractiveness higher and higher, you need to have information about people, what people want to find, what people do when they come. And till before this activity, all the decision was made over perceptions. Now we have some tools, and I asked Antonio to come and show you some vertical in a quick way, of course, because it's late. But to give you the idea on how we can measure the interest, the numbers of people, and how it's for us that has to manage this area, it's a real need to become more attractive for the future.
Thanks, Alberto. Well, as you introduced it, I mean, it was quite a challenging, let's say, project, because in the end, we were combining all together some problems that are coming from the sea, because we were asked to monitor, for example, the quality of water, or some information like sea water level, or the heat content of the water, or the quality of the water in terms of species and stuff like that, as well as also to combine this information together with, let's say, land information, so the building information that we were having connecting to the same dashboard. And so how we managed to do that? Of course, we put together a consortium of expertise. It's, local companies that they express quite a lot of experience in deploying different typology of services. So we thought about, the waterfront, the Porto Antico area, like a sort of connected infrastructure. So we are speaking about Internet of Things. So we were connecting everything that was already available. So in the area of Porto Antico, there were already some cameras that were installed in order to do some security monitoring. And so they became some sensors in order to understand which is the amount of people that are there. So we are also overcoming the problem of privacy because we are not looking at the faces, but we are counting the people that are passing towards a virtual gate that is in the area. So you have information about that. We were connecting other sources, Imonet, for example, because here in the area of Porto Antico, close to the aquarium, we have one of the oldest, actually, tide gauges in the world. So we are also setting the zero level of Italy in that place. So that data that is managed by the Navy is delivered to Imonet, and so we were able to consume this data as a local authority. So we put that data together. We consumed some of the forecast system that has been presented this afternoon by Francesco, because University of Genoa is doing an excellent job in order to calibrate and customize the weather forecast in this area. So we were able to integrate some short-term, high-quality, short-term, high-resolution prediction on the weather and sea component of the area. And so putting all this all this information together, we were able to set up, we also started collecting some information about some meters, some consumption that we have in the area. So we installed some meters in order to see how much water is consumed in the different buildings, how much energy is consumed in some other buildings, how much energy is produced, because there is a big parking area close to the aquarium as well, in which Alberto installed some solar plants. And so putting together all this information, then you may understand which is, the balance at the end of the day. But again, once we have access to data, once we have access to forecast, then you can also predict the amount of energy that you may have. So you can plan. Again, we are speaking about the decisional support system for a man that is really managing a quite complex area, because in the end, Porto Antico, although it's a big area, now it's even bigger and more complex, but it's like a small city in a city, because you have any kind of problems there. You have people that are living, you have people that are working, you have visitors, so it's quite a complex area. So it was quite challenging. And Alberto also mentioned it. We had also, somehow the challenge in order to make it even more attractive, also to tell about this kind of renovation and activities that we were doing in order to improve the quality of the long-term planning activities of the area. So together with all these systems that we were doing and collecting data, we were also setting up some, let's say, infologistic and cultural exploitation tools in order to disseminate some of the activity or to present some of the cultural heritage that we have in the area. So we were also using, again, also this system which we were using to provide, the visitors with the information as a sensor itself in order to have somehow an information about where the people are, how many people are in given areas. And this is, again, a kind of useful information also to plan better some of the information. And Alberto said, we are missing some trees in that area. And this is also a kind of information that we get from this statistical analysis, because you see that, hot days like today, you have no people around. They just fit inside places. So, in the end, the approach that has been done, and somehow it's going back to the topic of the day, is forward-looking and collaborating and planning with all the different stakeholders that are present in an area. So here, we have, different stakeholders that are living in this area, that is the Porto Antico area. But in the end, the services are not only for themselves, but also to other people. That I would say we can also do a sort of comparison with Imonet. When we say we invite people to share data with Imonet, it's not for Imonet's sake, but it's for the people that can consume data from Imonet. So it's a second level kind of invitation and sharing approach that we do. Because in the end, what we try and make it in practice is a user-centric model. Again, we have to think the stakeholder, but the final stakeholder are ourselves. So what else? Yeah, and this is just as before. This work, of course, it cannot be done by one single entity. We need to put together different expertise. As we were discussing the whole day, we need to have all the different voices, all the different expertise to be put together. And so here we had some experts in the artificial intelligence and image processing, some people that are very good in planning and management, people that are good in IoT and cloud development, people that are developing artificial intelligence in order to better understand which is the best use of rooms and spaces that you have. Cloud factories, you know us, and of course the university and the scientific component. So again, as a last message, I would say that we close somehow the loop that we started today, because we need coordination in order to satisfy the end user application. But this should be a sort of virtual loop in which we keep involving ourselves at different levels.
Just a final comment. Before I told you about perceptions, the system, the application, give us the idea that our perception 90% of the times are good. But the speedy of you have the data, and the speedy of the information and the suggestion you have with the dashboard is fantastic. It's really make the difference. And when you say we race with the future, we need to look to the future of the area, not in 2 years, but in 10, 15 years. And sometimes you may anticipate something thanks to look to the past, but you only need to look new things considering what is arriving around you. So it was very, very good experience. Thank you again, Antonio.
Thank you, Alberto.
Fantastic. Thank you very much, both of you, for this wrap-up. We closed the loop, we closed the day, but we didn't close the work. So I will not ask any questions from you to the speakers. Let's wrap up. I hope you can discuss in your private time, and you have already done this probably, and we'll do more. Just some final words. I would like to thank ETT and Antonio and Valeria for organizing this, for letting us be here, feet in the water, talking about marine knowledge value chain in all of its diversity. That's been fantastic. The city of Genoa, of course, the audience, the speakers, the online speakers. It seems to me that the regatta and the race and the marine knowledge race we are all in are sometimes having something similar, right? You need partnerships, you need team spirit, you need sharing and caring, and we need to work together, and I think we do, and we will do even more. Now we know even more of people who work in the same domain. They have the slogan, a race we can win, so definitely I think the future is ours, and we can win this race. I hope this for everyone. Thank you very much. Bye.
A couple of final logistic stuff. Okay, as you know, this is not the last day of events, so you're welcome to join us also tomorrow afternoon and Friday. Tomorrow afternoon, we are going to speak about some pollutants that may affect our sea. So we're speaking about acidification, we are speaking about underwater noise. And we are speaking about some technologies that can help us in order to mitigate and solve some problem. All have a multi-approach use of, locations that are already planned to be used, like, for example, the wind farm, because we can do a better and more sustainable use of our space. On Friday, we are going to have a nice session of cost-effective technologies in order to collect the ocean data. And so, again, we need data, share data. Please do follow ingestion. Last but not least, we have some fresh water, some fresh beverages over there, so I invite you also to help yourself over there. And so I would like to thank you all, and I want to give you a big applause.